This will be an introduction to force diagrams. So as we begin to investigate why objects are moving, we want to have a tool to help us to understand what is going on. What are the interactions that are responsible for the motion or for not having any motion to an object. So there are two pieces to any diagrammatic representation. The first piece is going to be the interaction diagram. The interaction diagram will have two specific elements. The first is going to be the object. In every force diagram, there is going to be a single object of interest. There may be many objects we're interested in, but when it comes to force diagrams, we can only show what are the forces acting on one particular object at a time. So first we have to identify in our interaction diagram, what is our object of interest? Then the next pieces we need, or there might be one or there might be many, is we need to know what is the surrounding environment. And the key here is that it's the surrounding environment that is going to be interacting with the object, and that is going to be causing any forces that happen to be acting on this object. So once we have our interaction diagram and we've represented all the pieces that we need to, that's when we can move to the force diagram. So to make sense out of this, we of course need an example. And the first example that we look at is going to be incredibly simple, but it's going to be very useful to help us determine what are the different elements here that we're interested in. So here we go. Our first example is a brick. So here we have this brick, and we're going to put it on a table or a cart in this sense. And what we want to know is what is happening to this brick. We have our object, but what is it interacting with? So keep this here. We'll try to diagram this scenario. So for the interaction diagram, we start by creating essentially a web of all of the different objects, well, one object, and everything that it might be interacting with. So we start with a brick. And we'll circle that and say, there we go, that's our object. Then we want to know what are the things that it interacts with. And the usual answers when this question is posed to the class is, one of them is that there is the table that is interacting. All right, that one makes sense. So we have the table. What else? Students usually say the air. The air is interacting with the brick. Air molecules are colliding with the brick, and there's an interaction there. So great, right, the air. The next one, sometimes I have to hint at, sometimes it just comes out, but that there is a gravitational interaction. So folks will say gravity, and I could write this. But the thing is, that's not the way to do it. We don't want to say what the forces are themselves. We want to say, what is this object interacting with? And the object is not interacting with gravity, but rather the source of gravity, which is the Earth. In this example, these are the three most important interactions that we could consider. Other things we can look at are the fact that there's lights overhead, the light is coming down and is striking the brick, so there are photons that are hitting the brick, being absorbed, heating it up, or being reflected to our eyes so that we can see it. So the light is here as well. So we have all these different pieces, and we have this object, this brick. So what are we doing with all this? Well, there's going to be an interaction between each one of these, and the interaction is two ways. So the air interacts with the brick interacts with the table, the earth interacts with the brick, the light interacts with the brick. But of course, all of these things are interacting with each other as well. The air is interacting with the table, the air is interacting with the light. That was a stranger one to think of, but it's also there. But the table and the earth are interacting. You can say the air and the light are interacting. The earth and the light are interacting. And then the light and the table. So we could keep making this representation more and more challenging. But before we go any further, we want to start identifying what these interactions look like. So the first one that I'm going to take is the interaction between the brick and the earth. This is the first one we want to consider what's going on here. So to write about any interactions, we can write about how does the force of one object interact with the other object. So for forces, we're always going to write F of A on B. And verbally, this is understood as the force of object A acting on object B. And for every one of the interactions that we look at, we want to write this force. So for instance, with the brick that is interacting with the earth, one way we could write this is the force of the brick on the earth. The question becomes, is the brick pulling upwards on the earth? And the answer is yes, actually it is. All objects with mass are gravitationally attracted toward each other. Now, we don't hold the brick and see the earth rush up to meet it. Instead, if we let go of the brick falls to the ground. When we get into some more details of forces, we'll talk about what's going on there. But the interaction is both ways. So we also have that the force of the earth is acting on the brick. So that is a bit of a cumbersome notation, and we're going to want a simplification. And in this case, we always write the force of the earth acting on some object simply as the force due to the gravitational field. So if I make some more room here, so the force the earth acting on the brick will simply be written as F sub G, which stands for force due to the gravitational field. To the gravitational field of Earth, to be specific. If we had two relatively equal mass objects in deep space, we'd have to come back to this conversation again. But right now, we're just going to consider that the Earth is just a really, really big object that is always going to be the thing that seems to be pulling down the smaller objects. All right, so we have one of our forces taken care of. Another interaction to consider is the force of the air molecules acting on the brick. We could also think about the force of the brick that is acting back on the air. But again, if we're just considering one particular object, then we just want to know what are the different forces on the brick itself. So another one we have here then is the force, the air on the brick. And if the brick were moving through the air, we might consider some kind of a frictional force, a drag force, as it fell. But since the brick is not moving, we don't have to think of that one. There's also a buoyancy force, and we'll consider the buoyancy force in more detail later in the semester, and how it is that water is able to support heavy objects. But for now, we don't need to think about water. We don't need to think about air, which can have a similar effect. We know the air can work in a buoyant fashion when a helium balloon is lifted through the air, it's because the air is somehow able to push on that balloon and lift it up. But here, with our brick case, this is not going to be a very large force. So the force of the air on the brick is negligible. So we're not going to worry about that one here. Another one, though, that is very important is the force of the table acting on the brick. And what we want to do is figure out, well, where is this force coming from? We always want to know where are these forces from? What do they do to? And a useful model for this is going to be going to a chemical model, where this is representing the molecular structure. So we have each little ball might be a different molecule. And then the springs in between are the intermolecular forces that are holding these molecules together. So when a brick is resting on a table, we can think of the table to be this set of molecules. And then we rest the brick on top. And what's going on? Well, the springs, the molecules and springs are being pushed down, but then there's a restorative force in those springs that's pushing back up. So what we know is there's an upward force here. The table is supplying an upward force so that the brick does not move through the table. And it's due to these intermolecular forces. Well, we don't want to have to write all of that down, but what we do want to do is have some sort of standardized notation for a surface, such as a table, that's pushing back on an object. So what we're going to do is simply call this a surface force. And it's going to matter what direction this force pushes, and it happens to be perpendicular to the direction of the surface. The surface is in the horizontal plane, but the force of these springs is pushing upward. So it's going to be a force that's perpendicular to the surface. So how we're going to write this is F, S, upside down T, our perpendicular side. We will call this the surface perpendicular force. Doesn't matter what our surface is, as long as the surface is pushing back on an object, we're going to simply refer to it as the surface force. Surface perpendicular force, I often just call it the surface force, but we'll write it with this particular notation. Okay, so these are the most important forces. We also talked about the force of the light on the brick, but that one is going to be even more negligible than the air in this case. So what we want to do here is we want to, first of all, simplify our interaction diagram, bring it down to the basic elements. And then we're going to work on the force diagram that will utilize these pieces. So simplifying the interaction diagram, we have the brick. We have the table. We have the earth. Draw these dual arrows. We know now that table acting on brick can be written as F surface perpendicular, and then the earth acting on the brick is F sub G. Now, as we're drawing our interaction diagrams, we don't always know which things are going to be negligible. We might just include them early on. So we might say, well, the air could be here. And then after considering the example in further detail, one might say, well, I don't think that's going to be important. So we can eliminate it. Maybe just erase that error there. Last piece is we want to identify what the object is that we're interested in. Because remember, we had all of these other arrows pointing between the different parts of the environment, because every part of the environment could also be an individual object that we might be interested in what the forces are that are acting on it. But here it's the brick. So I put a dotted line around it. And now my force diagram is going to include a force from each and every interaction that is present. So we start with our object. And I'm going to label these as our interaction diagram. And here's going to be our force diagram. So our object, the brick, is just going to be represented by a dot. In any force diagram, also called free body diagrams, we're going to take our particular object and figure where is the center of mass of that object. And we're going to draw a dot for that center of mass. Then we have the force of the earth acting on the brick. We know this is a downward force. So we draw an arrow that is downward, and we label this as F sub g. The other important force that we determined was the surface perpendicular force. We determined this force is going to be upward. But now we have to consider, how does the magnitude of that force compare to the magnitude of the gravitational force downward? And this can lead into a good conversation about, should the upward force be a larger force to overcome gravity? Should it be smaller? Should it be equal to the gravitational force? And usually nobody says that the upward force should be less, but oftentimes many people say the upward force has to be more. But it turns out in this case they need to be equal to each other. This is going to be true for any object that is not moving. If the object is not moving, then whatever downward force there happens to be must be balanced by an equal and opposite upward force. In fact, if there are many forces involved but the object is not moving, then there simply just needs to be a balance between all of those forces, such that the sum of the forces would net to zero. So once we have our force diagram, then we can come up with a mathematical expression. And these two go hand in hand. At times, the drawing of the force diagram is going to be aided by knowing what the sum of the forces should be. So for an object that is not moving, we know the sum of the forces should be equal to zero. So our notation for that, and this is going to be now a mathematical representation. Will be the summation sign. And the letter F for our forces. So the summation of our forces for an object that is not moving, and we have to consider the forces that are acting in all directions, is going to be equal to zero. For an object at rest. So we need to consider what directions these forces are in. There's both the x direction and the y direction. In this case, we only have the y direction, up and down, the vertical, to consider. But if there was also the x direction, and we'll see many cases where you have forces that are both in the horizontal and the vertical plane, then we would need a sum of force equation for each one of those. But for now, it's just the y direction. So we can write that the sum of the forces in the y direction, and we don't need the vector sign because now we are just specifying one direction, the y direction. And we can look at our force diagram, and we recognize there's an upward force. So using a coordinate system that has upward as positive, we'll say there's a positive surface force. And we add to that, and this is the sum of the forces, we add to that the gravitational force, which is downward. So we know this to be a negative force. Minus Fg. And we recognized immediately that with this object not moving, the sum of the forces must be zero. So we have a sum of force expression that can define this system. And from this, we immediately see that these two forces have to be equal to each other in order for this to equal zero. So in the end, we'll write surface force is equal to gravitational force. Now, that's a long process to come up with something that we probably could have made a guess at ahead of time. We didn't need to have any mathematical evidence to get us there. So the force diagram and the equation are in a sense redundant here. But there are going to be many cases that we look at that are going to have more than two forces. And when you have more than two forces, you may know what the relationship between them should be, but you don't know mathematically how they're related. And these expressions are going to be able to help lead us into some of the laboratories that we're going to consider so that we can begin to define the value of some of these forces. So to wrap things up, anytime that we want to consider an object that is in motion or an object that is at rest, if we want to understand why it's moving, we start with the interaction diagram. There's a certain object. If we look at what are all the pieces of the environment that this object is interacting with, and we sketch this out. And then from the interaction diagram, we see, well, what are the pieces that are acting on this brick? And from there, we can build this force diagram. And knowing whether or not the forces should be balanced, equal to 0, or whether they should be unbalanced, we need to think about that situation first. And then we can draw what the forces are, and from there we can put together a mathematical representation with the sum of force equation.